Welcome to Frequency Matters, the RF and Microwave Update series. I'm Pat Hindle, and today I'm talking with Erik Luther, Vice President of Product at CesiumAstro. Welcome, Erik.
Hey, thanks, Pat.
So there's been a lot of activity for commercial active phased arrays over the last few years. What applications are these systems being used for?
You know, phased arrays were first demonstrated back in 1905 by Carl Friedman Braun. And you know, those first demonstrations really proved that you could utilize multiple antennas to direct RF energy. But it wasn't until 2004 that the first integrated phased arrays were built into 180 nanometer CMOS. And it was demonstrated by Caltech. You know, that's less than 20 years ago at this point. And for a new semiconductor technology, that's really in its infancy. And when we saw 5G really start to take advantage of those types of ICs, as well as the 60 gigahertz Wi-Fi, it really opened up new doors in terms of what these semiconductor technologies could do. And as these processes have become more and more stable and more commonplace, we've moved towards processes that are naturally radiation hardened. And so in addition to these just traditional commercial applications, we're really excited about the potential to use them in high reliability applications, but using these commercial technologies.
So speaking of that, you know, what are the specific use cases for active phased arrays in the satellite and space market?
So when I look at space, you know, I really see space is being divided into three different areas. First, you've got to get to orbit, right? So this would be the launch segment. Second, we're trying to service users on Earth. And thirdly, we're trying to support different activities that are happening in space. So to break that down just a little bit, when you have a launch vehicle that's going up, you know, there's a lot of vibration, there's a lot going on. And so you need that launch vehicle to have connectivity while it's rising into space. And then as it makes its first orbits all the way around the Earth. And if you want to be able to transmit continuous video broadcast and things like that, you need to be able to create connectivity. And increasingly, the bandwidths of that connectivity are more and more demanding. And traditionally, omnidirectional antennas have been used. They allow you to send low quality video, I guess high quality in some ways, but low quality based on, you know, the 4K type standards we're used to now, as well as limited sensor and control data. Being able to use phased array technologies will allow you to sustain higher data rates and higher bandwidths throughout that full LEOP process as that launch vehicle is doing what it's meant to do, which is either enter orbit, bring people to orbit, or bring other payloads. When you look at servicing users on Earth, there's an opportunity to provide high data rate services to users, but there's also the data that's being collected from taking pictures or hyperspectral imaging. And being able to take that data and get it back to Earth is a huge bottleneck right now. Turns out that a lot of these companies that were doing Earth observation were really over the last few years trying to prove out their business model. You know, can I take data? Is there a customer? If I produce this data, can I get it back to Earth? Is it useful? And now that we're starting to hear a resounding yes, the next step there is to increase the amount of data that can be passed back to Earth, and to be able to pass data back to Earth while continuing to image, which means you don't want to have to body point the satellite at a ground station. And so there's a lot of opportunities where phased arrays and the ability to direct RF becomes important. And then when supporting space activity, when you start to look at where we're headed, in terms of the Artemis program, such as going to the moon, we're talking about robots doing lunar exploration. There's a recognition that the amount of minerals and mining that is done on Earth to produce batteries and our electric future and all of those types of raw materials are very expensive. And you may have rich deposits of those types of minerals in other places like the moon or on asteroids. And there are companies building business models to go gather those material, right? Tons and tons of waste rock are produced to produce a relatively small amount of useful material. And then perhaps you could bring that material back. And so because launch and because the ability to get to orbit and get to these locations is becoming more accessible, the first thing you need to be able is to be able to get there. The second thing that's really important is you need to be able to communicate. And so phased arrays are becoming interesting and exciting and useful in a really, really wide range of applications, even beyond 5G and some of the terrestrial applications that we hear a lot about.
So you touched on beamforming and beam pointing a little bit. What are the advantages of using active phased arrays in these applications?
That's a really good question. So phased arrays have been used a lot for radar. Being able to direct RF and then detect a return signal is a fantastic application for that type of technology. When you start to apply that to communications, it really comes down to the economics of the problem. Spectrum is a natural resource. We are, if you've seen the spectrum table from the FCC, which I know you have many times, but you realize that spectrum is all allocated and it's fairly expensive. The C-band auction drew something like $81 billion at 3.7 gigahertz. That's a lot of economic value that spectrum provides. And so anything we can do to use that spectrum more effectively is really important and valuable. So ultimately, active phased array, for anyone that might be watching that isn't familiar, is the use of multiple antennas. And you're essentially time delaying or phase shifting the RF signal at each one of those antennas so that it adds up or constructively interferes at an intended user terminal or at a directed location. And what that allows you to do is spatially divide an area, and you can transmit multiple beams to multiple users or multiple locations, each receiving their own independent data on the same frequency at the same time. And so that gives you the ability to really reuse the spectrum in a much more effective way. And so I think the question is less are phased arrays going to be used, and it's more a matter of when. Because they also have other natural things that they provide benefit on, and that they're naturally jamming resistant. I can actually create nulls on an interfering signal and just focus my energy on a particular location on the receive side. And as we start to utilize these phased array, the cost will continue to come down and they'll be more and more accessible. Certainly phased arrays are really advantageous at high frequencies where the wavelengths are small and the antennas can be small, and I can put lots of antenna elements in a particular location. But I think what we're going to see is that every antenna could potentially be a phased array in the future, as long as the space and the size and the frequency allocations make sense. And I think we'll start to see them even more prevalently in these applications where I really need to direct the energy and use that spectrum very efficiently.
And how are software-defined modular systems beneficial within the market for these active phased arrays?
Hey, that's a really good question as well. So phased array technology is really important, but it's really focused on the antenna and how you guide the RF energy. But when we look at modular, we see the antenna as a modular component, but we also are looking at up and down conversion. We're looking at the software-defined radio, the compute capability, and even the power supplies that are servicing that type of system. So when we look at that full system architecture, we recognize that for different types of applications, whether it's this lunar application or I'm working on a launch vehicle, or trying to provide data downlink, those phased arrays are fundamentally different in what they need to do, their duty cycle, so how often they're actually transmitting versus receiving, or maybe they're transmit only, the types of radio or waveforms that will be running on them, the amount of back off. All of these things contribute to how you might architect that phased array. And so being modular from a hardware perspective allows us to rapidly build up different phased array architectures to support our customers, sizing the array with a tiled approach for the actual phased array tiles, but then also the rest of that back end also being modular allows us to rapidly adjust the number of channels or the number of beams or what the power solution might look like. Now, that speaks to the modular part. The second really important piece that you asked was about the software defined. And so in addition to all that hardware being modular, being able to software define how the phased array performs, the modulation or coding or encryption that are being used, all allow you to meet these different application sets. So if you look at a lunar mission, you're typically working with NASA and you're baselining a CCSDS type waveform. If you're looking at high-speed data downlink, you're focused on DVB-S2X and a standard like that. As you look at multi-user support, you're starting to look at 5G or 5G non-terrestrial network type standards, which is a more advanced waveform using some more modern approaches. And so all of these can be serviced with a common set of building blocks if you're both modular and software defined.
Well, thank you very much, Erik, for talking with me today about active phased arrays and CesiumAstro's great approach with the software-defined modular solutions. We hope to have you back again for an update, and we thank everybody for watching Frequency Matters.